Hello and welcome to this presentation. My name is Sina Shaham and I'm presenting on behalf of the other authors, Professor Gabriel Ghinita and Professor Cyrus Shahabi. Let me start by giving a little bit of overview. So our focus in this work is on location-based alert services. In our system model, we have these users who have mobile devices with positioning capabilities, and they wish to be notified when an event of interest happens around them. We call such events alerts, and the area around an event is referred to as an alert zone. So alert zones are important in many applications, such as public safety. For instance, the user wants to be notified when there is an active shooting around him, or there is an accident or a fire nearby. There could also be commercial uses for these for location-based alert services. For instance, notify me when there is a sale or a live concert happening nearby. So this system is supported by a cloud provider to which users subscribe and periodically upload their locations. So clearly one very crucial problem that arises here is the issue of privacy. The cloud-based service provider may not be fully trusted, and it might share the data with third parties or take some sort of advantage of the data outside of the control of user. So it's really crucial to protect the user privacy. Prior approach in this regard were focused on k-anonymity and differential privacy. K-anonymity is shown to be not secure, and differential privacy by nature is not suitable for this scenario, as we are after precise and accurate results. So the user wants to know exactly whether he or she is in an alert zone. To this end, we use searchable encryption, specifically HV, to preserve the privacy of users in location-based alert services. All right, let's talk a little bit about hidden vector encryption, HV. So the user has this, the HV is based on the bilinear mapping and based on matching the indices, search on indices of the ciphertext and also the tokens. Let me explain what each one of these phrases mean. So we have this user with the message, and associated with the message, we have this index. On the other side, we have the trusted authority, and it knows about the alert zones, alert styles, and their associated indices. The trusted authority is a party that has, for instance, the Center for Control of Diseases or different trusted parties that government parties that may exist. And what it does is to generate the public key and the secret key. And it shares the public key with the user. User will encrypt this data using the public key, generating a so-called ciphertext. And on the other side, the trusted authority also encrypts its data using the secret key, generating a so-called token. Both sides send their data to this service provider in between, which is the cloud-based service provider, which does the most of the computational complexity over there. And what happens there is that if we have a match between the index of the ciphertext and the token, the message will be revealed. So for instance here, as you can see, the indices match, so the message is revealed. If we do not have a match between the index of the ciphertext and the token, what happens is that a special character is returned and no further information is gained. Let me have another example here. So here we have an example in which we do not have the match. So what happens in this scenario is that a special character returned and no further information is gained by the server. Another very important advantage of HV is the introduction of a special character called like star bit or wildcard, which works as like a don't care bit. So it gives us a match with 1 and 0. So both of 0 and 1 matches with the star bit. So here, when the matching process is conducted, we do get a match and message is revealed. Let me have an example in which we do not have the match. So here the star bit gives a match, but in the last bit we do not have a match, so no information is gained by the server. It turns out the complexity of HV is proportional to the number of non-star bits in the tokens. For instance, let's look at this token that I have on the slide as an example. So you can see that the first and the most, the least and the most significant bits are non-star bit, and those are the ones that result in the computational complexity. Okay. The previous approach in this regard was using the gray encoding on the grid to reduce the number of non-star bits. So our goal is basically to reduce the number of non-star bits so we can have less computational complexity. However, in that work, the computational complexity was still high. So motivated by this fact, we aimed at this work to reduce the computational complexity and improve the performance of the system. You can find the reference on this paper that I've mentioned on the slide. Okay, let me now put the HV in the context of a spatial domain. So we have this grid. Each cell of the grid has an index representing that cell. Some of the cells are alerted. And again, we have the server and the trusted authority. The trusted authority knows about the alerted cells. And the way that a special character is generated here is using the logic minimization. So these indices are passed through the logic minimization. This can be done using the several tools available online. So the underlying idea is just the kernel maps. For instance, one tool would be the Espresso, which is available freely online. And the way we do it is using a library in Python. Next, the generated tokens, basically the data will be encrypted on the trusted authority side using the private key generated by the trusted authority, and the tokens are sent to the server. On the user side, we have this user moving around, and it's subscribed to this location-based alert service, and it wants to be notified when he or she is in an alert zone. So here, what it does is that when it's updating its location, it will encrypt its data using this public key shared by the trusted authority and sends it to the server. And if there is a match between the indexes of the index of the user and the tokens, then the user will be notified that yes, you are in an alert zone. But otherwise, no further information is gained by the server. So that's the key point here. The server learns nothing if the user is not in an alert zone. Now, how can we actually minimize the number of non-star bits in the token? So we are giving these indices on the trusted authority side. We are giving these indices to the logic minimization, and we get this output combined indices, and we would like to have higher number of star bits and lower number of non-star bits, basically. So we would like to see more combinations between indices. Let's have an example here. We have this 2x2 grid. We notice that in the spatial domain, we do have these probabilities of cells becoming alerted. So we know that, for instance, if we are in a crime zone area, there is usually a higher chance of a cell becoming alerted, but if you live in a safe neighborhood, there is, for instance, less chance of that cell being alerted. So what we did was to associate each one of these cells with a probability. This probability indicates the likelihood of that cell becoming alerted. And we turned the problem into an encoding problem. So what is the best encoding of this grid that actually minimize the number of non-star bits on average when they are passed through the logic minimization? Let me mention a very quick point here. We suppose that there is no correlation between cells becoming alerted. The algorithms that we propose in our work are actually independent of this assumption, but we do use this assumption in the extended version of the paper. Just to review the problem statement, find an encoding of the grid that reduces the number of non-star bits in the tokens generated from the alert zones. Okay. Let's have a look at this token. So we have this token at the top, 0, star, star 1. And these are the indices in the ciphertext that actually will give us the match. We started by trying to making the indices that give you a match a unique sequence. The way we did that is to apply gray encoding on the star bits. So if you look at it here, we have the gray encoding on the 2 stars, but not any kind of gray encoding, but the one that starts with all of them being 0. Doing so, each token maps to a unique series of indices. Knowing about this gray encoding, it suddenly reminded us of this K-cube, this hypercube. In the hypercube, 2 nodes are connected if and only if their Hamming distance is 1. We've proved that there is an onto this bijectional mapping between cycles on the K-cube and each token. For example, let's have this token as an example. We have 0, star, star 1. This maps exactly to this particular cycle that we show on the K-cube. And remember that the order is unique. So this having these assumptions turn the problem into a graph embedding problem. So if you look at this K-cube, you notice that what we want to have is that we would like to assign these indices to the grid cells such that we have more combinations, right? Which means that we would like to see a larger cycle. We would like to have higher probabilities for the cycles. So we would like to embed this K-cube in a complete graph. This complete graph is the representative of the grid itself. So for each cell on the grid, we have a node there. We would like to do it such that a probability of generation of loops are maximized. And that's the point where we prove in the paper that this embedding problem is NP-hard. Knowing that the problem is NP-hard, we wanted to find a good heuristic algorithm to approach this problem. Our proposed method is called Gray Optimizer, and I'm going to explain it here. So the way we do it, we try to maximize the probability of cycles on the K-cube with respect to a particular assigned seed. So for instance here, we assign the cell with the highest probability to this particular index in which we have all zeros, and we take a step-by-step approach to towards assignment of all the cells on the grid. First, we focus on the ones with the Hamming distance of 1, then we move to the ones with the Hamming distance of 2 from the seed, and finally we complete the graph or complete the assignment. Let's look at in more detail what happens here. So in the first step, we would like to assign the ones with the Hamming distance of 1. Note that the combination of the C1 and any of these ones with the Hamming distance of 1 is a single star bit and the rest of them are non-star bits. So here, the way we do the assignment is to choose 3 cells of the grid from the that have the highest probability, and we aim at assigning them such that the probability of their combination, this one shows the cycle of length 2, so because this is the initial point, starting point that we have. So we do it in a way using dynamic programming to maximize the probability. So we find the optimal assignment here. The algorithm that we apply is called Hungarian algorithm, and which results in the optimal assignment of the nodes. Then after the assignment of the ones with the Hamming distance of 1 from the seed, we move to the ones with the Hamming distance of 2 from the seed. Let's look at it here. So for instance, consider C1, C3, C5, and C2. If you look at the indices, you can see that by applying these 4 indices to the logic minimization, you actually get 2 star bits and 1 non-star bit. And the process of assignment is quite similar to the first one that I explained. So we choose 3 nodes of the complete graph with the highest probability, and on the other side, we try to assign them such that we maximize the probability of cycles, and it is done using the dynamic programming and Hungarian algorithm. We continue the same process until all the nodes are assigned. Okay. The complexity of algorithm, just focusing on the without the dynamic programming, is actually n log of n, but including the dynamic programming, the complexity becomes in the order of n log of n to the power of 4. So the question is it suitable for grids with higher granularity? As you can see, the probabilities are quite small, so the probability of large cycles becomes really small, and also results in high computational complexity. So we would like to, for large cycles, the grids with higher granularity, we would like to have alternative approaches or modify the gray optimizer such that we can apply it on the large grids. Our proposed solutions in the paper are 2 algorithms. The first one is called multiple seed gray optimizer, MSGO, and the second one is the scaled gray optimizer. So both these approaches indeed work on 2 factors. The first one is the number of seeds on which we apply the gray optimizer. So instead of just applying the gray optimizer with respect to a single seed, we aim at applying it with we aim at running the algorithm using lower depth, but having multiple seeds. And the second factor is obviously the depth that we are playing around with. For the MSGO is based on a cluster-based approach. So we select the seed and apply the gray optimizer on it with a lower depth. And these depths are based on the user preferences. So you can have grids with different clusters with different sizes. This application is actually quite suitable for scenarios in which we are trying to reduce the computational complexity, let's say, for 2 different organizations. And for each one, we would like to have a lower computational complexity. And the second algorithm is called SGO. So the SGO algorithm was inspired by the BFS graph assignment, and in this algorithm, we indeed run the gray optimizer on all of the nodes on the grid. So all the nodes become a seed to the gray optimizer. The depth of the gray optimizer is set to 1, but you can actually use higher depths as well. We use the depth of 1 because it results in the lowest computational complexity, which is quite suitable for large grids. So for instance, here I have it with the depth of 2. So we apply it with we apply the algorithm on the first seed, C1 equal to all zeros, and after finishing that one, we move to the its first neighbors. So the ones with the Hamming distance of 1 from the seed, we apply the gray optimizer on the first neighbors in a descending order of probabilities, and we continue the same process until all the nodes are assigned. So let me give you a summary of the algorithms that we've had and their computational complexity. So the main algorithm is the gray optimizer, which is the root, and it is applied on it's suitable for low granularity grids and has the complexity of n log of n to the power of 4. The MSU is suitable for medium to high granularity. That's the cluster-based approach, and depending on the given depth to the algorithm, it can have different complexities, but at least it will have the complexity of n log of n. And the SGO algorithm is the one which is suitable for large grids and has the complexity of n log of n. Very brief. So we applied the we had this comprehensive experimental evaluation section, and we used the algorithms with different depths on different grids with different sizes. And another defining factor for the algorithm is the initial assignment of those probabilities to the cell. So how we assign the initial likelihood of cells becoming alerted. The way we do it is to use the this function that I have, the logistic function. The reason we are using it is that it has two parameters and gives us this flexibility to try the algorithm for different distributions. So on the experimental section, we apply the gray optimizer on grids with low granularity, 100 cells, MSU on medium granularity, 1024, and the SGO on very large grids, which was not actually possible previously. On the x-axis, you can see the percentage of in all the graphs. So let's consider the first column first. So we have two graphs, and we examine the algorithm gray optimizer, and we show the number of HV in terms of the number of HV operations that we have and the improvement that we achieve. On the x-axis of the graphs, you could see the percentage of alerted cells. So if on average we have, let's say, 20% of the cells are alerted in this scenario. So we show the number of HV operations required for the gray optimizer, and also we compare it to the previous work HG that I explained in the beginning. And in the second graph, we actually calculate the percentage of improvement. So doing so for all the algorithms, we showed that on average we are improving the performance by up to 50%. But it depends on the depth and the initial assignment of the probabilities and the number of alerted cells on the map. So these factors need to be considered to get the final result. But overall, the performance improvement is really good, and it can achieve us up to 50% improvement in the computational complexity. Let me have the concluding remarks here. So we introduced this novel transformation of a spatial domain into this context of graph embedding. So the main contribution is to transforming the problem of reducing the HV operations to this graph embedding problem, and showing that this problem is indeed NP hard. Knowing that the problem was NP hard, we proposed this strong heuristic algorithm called gray optimizer. We wanted to apply the gray optimizer for large grids as well as the low granularity grids. So we proposed two approaches. The first one is the MSGO, which is the cluster-based approach, and the second one, which has the lowest computational complexity, is called the SGO. And we showed that on average we achieved the performance improvement of 50%. So we reduced the computational complexity by up to 50% for different algorithms that we propose. Finally, I would like to thank you all for listening to this presentation, and please let us know if you have any questions. Thank you very much.